Every what is that?
Good morning, everybody. Please, if you can hear me, hello, please, let me know if you can hear me on the chat box. Can you please go to the chat box and notify me if you can hear me? Thank you. Okay, thank you so much. Now, this is CHM 121, and my name is Dr. Drake Eze. I will be taking you for today's lecture and the next two lectures on physical chemistry as a part of CHM 121 lecture. Now, before we start the class, I would want to make some kind of plea to all of us. Now, in this class, I would appreciate it if we will have our biros or our pens and paper. Though it's an online class, but I will need us to write because we'll be having a lot of class activity. Now again, I will be asking questions in class and I will expect you to go onto the chat box and give me your answer. And I will be noting down names of students that are answering my questions. In this regard, please make sure that you log in with your real name. I don't want to see something like iPad this and iPad that. So if you don't have your real name as your login detail, can you please change that now? So I will be able to know who it's actually who I'm talking to. I'm not talking to a robot. Now that is by the way. Now again, I will also plead that will remain silent as the lecture goes on. If you have any questions, please just put them down. There's going to be a provision for us, even the other lectures, they will come around to answer our questions. Maybe the last day of the lecture, probably next week, Wednesday, where we will attend to students' questions. I know today's class is 10 to 11 because the number of participants I am seeing here it's 4. The official class, is it 10 to 11 or 11 to 12? Please answer me in your chat box. Thank you. What's the official time for the class? It's 10 to 11. Okay, thank you. I'm just seeing a few students log in. What's the problem? Okay, so today's class, I'm going to take off on can you see my slide? Okay, yes, thank you so much. We'll be talking on heat of reaction and measurement of heat changes. Now, before we go on, I want to bring our mind to, what happens in a chemical process.
Let's go.
Please, I don't want, please, can you just mute yourself? Don't disturb my class. Dr. Gumbiade, please, can you help me meet all the students? I'm trying to do it from here, but I'm not getting it.
They are all muted.
Okay, sir. Thank you so much, sir. So I want to bring to our mind what happens in a chemical process. Now, our elementary chemistry, we were told that if two substances react under a suitable condition, that a new substance will be produced. And the materials that come together to give us the new products are called the reactants. And we now call the new substance our product. And so we can say that when we have two or more reactants coming together, that a new product is obtained. Now, for the product to be formed, something happens. Bonds are broken in the reactant parts, and new bonds are formed when the products are, and new bonds are obtained when the products are formed. That is what we know in our elementary chemistry. And what this is, again, what happens in any chemical reaction. Now, due to the breaking and formation of new bonds, there are bound to be changes in the chemical energy when a chemical reaction occurs. Now, this change in energy is referred to as heat of reaction. So the change of energy that is released or the energy that is released or absorbed when chemicals are transformed in a chemical reaction is referred to as heat of reaction. This heat of reaction describes the energy change content when the reactants are converted into products. We are still saying the same thing. So let me further explain them. Let us picture a chemical reaction setup where the reactants and the products represent our system. And I know that in our previous lecture, we've discussed what a system is and what a surrounding is composed of. So this is not the first time we are hearing it. Now, let us picture a set of reaction, where you have your reaction in your secondary school lab. The reactant and the product. we want to refer to them as the system. Then every other thing will make up the surroundings. Remember, every other thing might be the beaker that you're using, the thermometer, the condenser, and all of that. We're going to refer to them as the surroundings. Now, two things are possible in this. The two things possible is that heat can flow from the surrounding to the system. And if heat flows from the surrounding to the system will know that automatically will absorb the heat, and therefore there's going to be a change in enthalpy. And this change is referred to as this change is what we call the endothermic change, or endothermic reaction. Now, here, energy is required to keep the reaction running. And when energy is required to keep the reaction running, that means that we have our delta H, which is change in enthalpy positive, and that is what is referred to as endothermic process. If you look at the picture on the slide, you can see the arrow here that heat is going into the system. Remember, I told you there is the reactant and the product that we consider as system. So heat is flowing from this surrounding. It's flowing from your surrounding to the system. And when this happens, the change in enthalpy is positive, and that is what endothermic process. Another thing that is possible is that heat can also flow from the system to the surrounding. Now, when there is a release of heat to the surrounding, the enthalpy change is negative, and this process is referred to as exothermic process. So we have this here in the slide as representing the exothermic reaction and the endothermic reaction. But we want to see how this is represented when using a chemical equation. How do you represent the enthalpy change, that is the endothermic and the exothermic process, when describing or writing a chemical equation? Now, looking at these two equations we have on the slide here, we have the first equation as the reaction of hydrogen and chlorine gas to give us hydrogen chloride. Now, delta H is a negative, has a negative sign. That is, you have minus 188 kilojoules. That is the delta H. What this is saying us is that delta H is what the process is what is exothermic. Now, the second reaction here is the CO2 giving us this carbon and oxygen, while your delta H is positive, and that represents an endothermic reaction. Here, heat is released when it is exothermic, and heat is absorbed when it is endothermic. That is when it is positive, when the delta H is positive. Having understood the representation of delta H, or the change in enthalpy using chemical equation, we can as well look at the thermochemical equation. In thermochemical equation, the heat absorbed or released is treated as a reactant or product. It is treated as a reactant or product. Look at this first equation. You have your reactant here, you have your product here. Here we're just showing the change in enthalpy. But when we are describing this using the thermochemical equation, we would include the change in enthalpy as a reactant of a product. In that case, let's look at the first equation again. Here we have our the process as an exothermic process, and hence our delta H is negative. If delta H, if the process or the reaction is an exothermic reaction, that means that the heat release is treated as a product. If it is exothermic, the heat release is treated as product. So for this particular equation, now you have the heat release as here in the product, which is plus 188 kilojoule. But if the reaction is an endothermic reaction, The heat released is treated as a reactant. And so you have here CO2 plus the heat absorbed will give you the product. So that is the way you represent the using a thermochemical equation. So we'll describe these two equations, the chemical equation and the thermochemical equation. So we'll know how to represent the heat change of a reaction. Now, the next one we want to look at the different terms of heat of reaction. Reactions of when there could be either a combination of two substances or complete combustion of a substance in oxygen to give a new one, or you could have a substance being dissolved in a solvent to give you a new thing, and all of that. So that is what we want to look at. What do we call the heat that is released or absorbed during all of these reactions? The first one we want to look at is, but let's first also remember that the heat of reaction changes are being expressed based on the type of reaction that the reactant undergoes. One is the heat of formation. The heat of formation describes a change in enthalpy that takes place when 1 mole of a compound is formed from its element. 1 mole of a compound is formed from its element. Now, you have here, you have 1 mole of HCl being formed from its element, that is hydrogen and chlorine molecules. They will give us 1 mole of the product. So the heat of formation is denoted as delta H of subscript X, and that is minus 22.0 kilocal, showing us that this actually is an exothermic reaction because delta H is what is negative. So 1 mole of a compound is formed from its elements. You call the heat, the change in enthalpy or the heat change, heat of formation. Now, the next one that we want to look at is heat of combustion. For heat of combustion, it is the change in enthalpy of a system when 1 mole of the substance is completely burned in excess of air. And when we talk about excess of air, we're actually talking about excess of oxygen. So it will be air, it will be oxygen. Now, the heat of combustion, for example, we have the heat of combustion of methane. When you have methane plus oxygen to give you your carbon dioxide and water. The heat change for this particular reaction is referred to as heat of combustion. And this is denoted as delta H subscript C. So we don't have it here, but when you get your slide, you will see all of this. Now, the next one here is heat of solution. What do we mean by heat of solution? The heat of solution is the change in energy when 1 mole of a substance is dissolved in a solvent, so that further dilution does not give any change in enthalpy. For example, you have your sodium chloride, which is your ordinary salt. You dissolve it in water, you will get sodium chloride solution. We form a solution of sodium chloride. Now, the heat that is involved there, or the heat change, or the change in energy for this particular reaction is referred as heat of solution. Now, there is something I want us to note, and I will go back to heat of formation because that is what you have here on the slide, and you will understand it better while I'm explaining it. Now, let us assume that hydrogen plus chlorine gas gives us HCl. Another way we can balance this equation is by what? Is by having, if we have 2 moles of HCl. So we have H2 plus Cl2 to give us 2 HCl. I hope you guys are following me. Now, if this happens, the enthalpy, the heat of formation is not going to be minus 22.0 kilocal because it is 2 mole of the compound that is formed and not 1 mole. Remember, the definition says change in energy that takes place when 1 mole of a compound is formed. When 1 mole of a compound is formed. So 1 mole of HCl being formed from a combination of hydrogen and chlorine gas, the change in energy is going to be minus 22.0. So if I balance the equation by removing this half here and this half here, I'm now having 2 moles of HCl. That means I'm going to multiply this by 2. So it's going to be 44.0 kilocal. I hope you guys are getting me, because I am talking about 2 moles and not 1 mole. So automatically, when I want to get the heat of formation of HCl, which is just heat for 1 mole, I am going to divide minus 44.0 over 2 to get minus 22.0. So the same thing applies to the heat of solution. If you look at the heat of solution, the definition says that it is the change in energy when 1 mole of a substance is dissolved in a solvent. So if you have 2 moles of a substance being dissolved in solvent, remember that whatever that you have as the heat of solution, you're going to divide it by 2. Because what is required, what this heat of solution is 1 mole of a substance and not 2 moles of a substance. And I hope you guys are getting me. You understand what I'm saying. Now let's go to the next one, which is heat of neutralization. Heat of neutralization is actually the change in energy of the system when 1 gram equivalent of an acid is neutralized by 1 gram equivalent of a base. Or you can say that when 1 gram equivalent of a base is neutralized by 1 gram equivalent of an acid, to be vice versa in the dilute solution. In that way, the heat change in this particular reaction is referred to as heat of neutralization. Now, the reason why we are taking time to describe all of these types of, heat of reaction is because we will be making use of them when we'll be looking at our application of Hess law, which is our Bonhoeffer circle. We will be looking at all of these heat changes, because that is what we'll be using to note the heat change for any particular reaction, so that by that time, it won't be like a new thing to us who have an understanding of what it's all about. Now, for this heat of neutralization, I think that is what we know, so we are not going to waste time on that. We have your HCl plus sodium chloride, that is the common one, which will give you your HCl plus sodium hydroxide. HCl is an acid, sodium hydroxide is a base. You have sodium chloride and water. If you look at what is happening here, you see that you have the reactants giving you the forming 1 mole, giving you 1 mole of the product. But the basic thing, the most important here, is that you're using 1 gram equivalent of this. So you look at their masses, it's going to be, if you want to weigh, this is going to be 36.5 grams of this. So I think this is 23 plus 16 to 40 grams of sodium chloride. So when you dissolve it, the equivalent, that's 6 grams of HCl and 40 grams of sodium hydroxide are equivalent, because we are looking at grams. So when you dissolve it in the water, the heat change, or the change in heat, is going to be minus 13.68 kilojoule. Now you have other examples here that you can look at because of time. You have your heat of fission. The heat of fission is the change in heat content when 1 mole of a solid substance is converted into the liquid state at its melting point. For example, you have your ice water and it melts to form a liquid water. That is the heat that is released, or the heat change in for that particular reaction is referred to as heat of fission. Now, we want to look at the next topic under today's lecture, which is measurement of heat changes. We have described some types of heat changes. How do we measure this? How do you measure that reacting one equivalent gram of HCl, and that was sodium hydroxide, give you the sodium chloride, and that the heat change, or the change in enthalpy is minus 13.68 kilocal. How did you come about that? You came about that by measurement of the heat changes. And that is what we want to describe now. How do we go about this? Now, one important feature of a reaction is heat absorption or release of heat. And for this particular thing, to measure the heat change, we use what we call a calorimeter to measure the heat change in form of the enthalpy. Now, remember that we have the energy flow from a reaction, and then we measure the enthalpy change of the system. So let's look at some examples to understand this better. Okay, before we go into the examples, there are some units that we need to understand, or some terms that we need to understand that is applicable to measurement of heat changes. Now we look at the first one is the unit for heat. The unit of heat can be in calorie or it can be in joules. Let's go back to this slide. Here I have kilocal. Now, if you look at here, I have kilojoules. So it could be measured in this unit, joule or calorie. Now, how do we look at these two? These two, they have the conversion factor for these two. So you can actually convert one to the other. You can convert your joule, you can convert your joule to your cal. So that is not a problem, regardless of the unit that is being used, because there is a conversion factor. Now, 1 calorie is equal to 4.184 joules. That means that to every 1 calorie, you have 4.184 joules. So you can be able to do all the conversion at any time that you want. What we have here as an example is to convert 6.1 calories to joules. Then 1 calorie to 4.184 joules. 60.1 will give us a higher number of joules, and that is 251 joules. So in that way, you can also convert back your joules to your calories, so you still get the same thing. So with this conversion factor, we don't have any issue, regardless of the unit that we are using and regardless of the unit that we want to convert to. Now, the next thing I want to look at is the factors that affect the energy required to change the temperature. Now, the amount of substance being heated, that is the amount of a substance, will affect the heat or the energy. The temperature change will also affect it. And the identity of the substance, because the identity of the substance will also give us the specific heat capacity. It will tell us the specific heat capacity of that substance. Now, let's look at what we mean by all of these things. How do we apply this to calculation of heat changes? In application to calculation of heat changes, we need again to define two important terms: the heat capacity and the specific heat capacity. The definition is here. I'm going to dwell with the specific heat capacity, which is what is commonly used. The specific heat capacity is the energy required to change the temperature of a mass of 1 gram of a substance by 1 Celsius degree. I don't want to go into intensive property and all of that. We have done that with the other lecturers, where you classify all these terms either as an expense or intensive property, but that is not what we are looking at today. Sorry, I did not. So before that, we have the specific heat capacity of some common substances. Now, remember that we looked at some factors that can affect the change in heat of a particular substance. We said the mass of the substance, the temperature change, and the identity of the substance. I want to explain what we mean by identity of substance. Remember, I said that has to do with the specific heat capacity of a substance. Now, we have water. Water can exist as a liquid, as an ice, or as a steam. When we mean steam, you know when water is hot, that is gas. Now, if you look at this, all of these, they are water, but in different identity. In different identity with different specific heat capacity. That is what I don't want that. I don't want that. I don't want that again, please. That is what we mean here when we say sorry. I want to go back. So that is what we mean here when we say the identity of the substance is also affects the heat change or the energy change. Now, how do we do the calculation then? To calculate the energy required for a reaction, the formula is as given here. The heat required is equal to the specific heat capacity of the substance multiplied by the mass of the substance multiplied by change in temperature. Now, this heat change is what we are. Remember that it's same thing as the enthalpy or the change of heat is regarded as delta H. Now, delta H can be obtained using this formula. Looking at some examples, the first example here is calculate the amount of heat change. Now you specify the unit to use in joules. So if you calculated calorie, or if you have your heat capacity, because your heat capacity has a unit, the unit is in joules per gram degree Celsius. As if you can ask this question, as if you calculate the heat change in calorie. That means that after calculating the heat change, you need to convert to calories because that is what the question signifies. But in this case, we are good to go. The question says calculate in joules, and the specific heat capacity is in joules per gram Celsius. So we don't need any conversion. I hope you guys are understanding. Can we go to the chat box now? Is it clear? Yes or no? I'm on the chat box. Can I get your answer? Can I get your answer? I have one no. I have four clear yes. I'm having yes. I have just one no. But that just one no is so important to me that I have to go back again. That's one person said no. I will need to go back so that the person will understand what we are saying. But let's go back to okay, here. Now, whoever that says no, are you seeing what I am showing you here? The unit for this is your specific heat capacity for the water. Now, because the water is in liquid form, that is why we chose this specific capacity. Remember that we have different identities of water that we can, with different specific heat capacities. Now, for this particular one, it is liquid water in liquid form. So we are using this capacity 4.184 degrees Celsius. As I can see from this question, calculate the amount of heat change in joules. I would have asked you to calculate the amounts of heat change in calorie because you can have your heat either in calorie or in joules. We have already defined that long ago, so we don't need to go into that. Now, and I am saying, if that is the case, if I have changed this joule to calorie, because you have your specific heat capacity unit in joule, just go on to calculate whatever you're calculating as we have here. But remember, you're not going to leave your answer in joule. You're going to convert your answer to calorie because my question is in calorie and not in joule. But for this question, because we have our answer, we have been asked to leave our answer in joules. We don't have anything to convert again. I hope the person that says no has understood what I'm saying. Now the question says needed to raise the temperature of 6.25 grams of water from 21 degrees Celsius to 30.0 degrees Celsius. Now this particular question is a straightforward question. You don't need anything here, any explanation. We already know the specific heat capacity. The specific heat capacity is by default. It's not what you calculate. It's a known value. So it's not it's not something you every and will be different. Now we know that the formula is the specific heat capacity times the mass multiplied again by the change in temperature. We have this question, the mass. We have the temperature change. The temperature change is the difference in temperature, that is the increase. Now, what information do we need? The information we need is the specific heat capacity, which we have been given here at 4.184 joules per gram per liter. Go on to the question, and the answer is 471 joules. So that is the amount of heat that is needed to go from this 20 degrees Celsius 39.0 degrees. Remember, the factor that can affect heat and change energy is the mass of the substance. So if I increase the mass, if I increase the mass of this, if I increase or decrease the mass of this water from 6.25 to another thing, either higher or lower, it is going to affect this amount of heat change. Another thing again that can affect it is what? Is the increase in what? Change in temperature. If I change any of these temperatures now, any of them is going to affect the amount of heat. Then the last thing that will affect the amount of heat energy is the identity of the substance. If I change this water, solid water, which is ice, or gaseous water, which is steam, the specific heat capacity of steam is 2.0. Automatically, the amount of heat gain will change. So that's what the amount of heat gain for any particular substance. The identity of the substance is represented in each specific heat capacity, the mass of the substance, and the change in temperature. Let's see. Now there's an exercise here. The question says a sample of pure iron requires 142 calories of energy to raise its temperature from 23 degrees Celsius to 92 degrees Celsius. What is the mass of the sample? Now we are given the specific capacity of the iron. Now we require mass. Can we quickly do this? And let me have the answer on the chat box. I'm giving out just 1 minute. Let me have the answer on the chat box. You know what to do. Quickly. Done. Has anyone got the answer? 19 grams. Good. 19 grams. Excellent. 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 Anyone? Does anyone have any other answer aside from 19 grams? Please let the team know so that I will know how to help you out. So these are the answers here, and then we have that sorted out. First of all, remember you have to convert your calories. We do that. Excellent. Excellent. I'm giving all your work. Yes. And that's a great one. So you have that. Because it's only when you convert it that you get 19 grams. If you don't convert it, you cannot get 19 grams. So for those of us that are using 1.2 calories straight on, you're not going to get 19 grams. You're going to get something different. So please, that is the Now let's go to another concept check to know how far we understood it. I'm not going to waste too much time on this because I don't think we just have about 22 minutes. This is a question you can that this is just a concept check, so the answer is given to you. and this other one. It's not the same thing. Since you're able to do the 19 gram phone, I think that's the most difficult one. The other one can actually get them done. Now we look at this other one. We have a reaction here. This is an equation. Remember, we can represent our change in enthalpy using a chemical equation. So we have a chemical equation here, and we have that delta H is minus 296 kilojoules. Now, if we have this, the question says calculate the quantity of heat released when 2.10 gram of sulfur is burned in oxygen at constant pressure. Now, what is the type of heat? Can you write that on the chat box for me? We have a substance that is completely burned in oxygen. What do we refer as this delta H? What is this delta H referred to as? Kindly give me my answer. I'm going to the chat box now. Heat of what? Heat of what? You can't hear me? Can you hear me now? Sorry, can you hear me now? Can you hear me now? What's happening? It's not loud. Okay, let me check my. But it's loud. That happened. Okay, is it louder now? Can you hear me? Okay, someone said yes, ma. Thank you so much. So can you answer my question? And I'm going back to the question. We have a question here. Calculate the quantity of heat released when 2.10 gram of sulfur is burned in oxygen. And I don't need you to answer the question. What I need for you is to tell me what type of heat change is this? What type of heat change is this? Write that on the, in the chat now. I want to see it in the chat. Heat of what? Heat of what? Good, good, good. I need more answers. I need more answers, please. Good. Heat of what? Combustion. Correct, because we have the substance burning in what? Oxygen. It will be oxygen or air. Now let's now do the calculation. We have to calculate the quantity of heat is when 2.10 gram of sulfur is burned in oxygen at constant temperature. Now, listen to me. You have your Bible with you. You're going to write now. I am not seeing you, but you need to write. You don't know when I will ask you for this. We want to determine that is the for the reaction of 2.10 gram of sulfur constant temperature. What and what do we know? Now, we know that when 1 mole of SO2 is formed, when 1 mole of sulfur oxide is formed, that we have minus 296 kilojoule of energy released. So the energy that is released when 1 mole of SO2 is formed is minus 296 kilojoule per mole. I am going to take it step by step so that some people take time to understand some certain things. So let's go step by step. I know that those of you that are smart have already known what to do, but let us help every other person. Now, we have 2.10 gram of sulfur. Remember that 1 mole of sulfur is 32.0 grams and not 2.10 grams.
Ma, we can't hear you clearly again.
Maybe it's from your end. I don't have any issue here. And I've not moved from where I am. Maybe it's the network. Can you hear me? Hey. Wow. And I raised it to the. Okay, let's see. Don't want to press anything and this thing will go off. Can you hear me now? A little. Okay, I know what to do. Can you hear me now? Can you hear now? Ah, okay, let's work on this before we start. Okay, don't worry. Don't worry, don't worry, don't worry. I know what to do. Just calm down. I'm just looking at the turn up volume. Let me know when you can hear me well. Can you hear me now? Just hold on. Let me see if I can. Let me use the phone and just hold on. Can you hear me now? Is it better? Hello? Hello, can you hear me? Can you hear me now? Not clear. Okay. I want to see more of
Breaking.
saying I don't know. I have the highest volume in my, and I don't know. I've not changed anything in this. I've not changed anything here. I've not changed anything in my own system here, so I don't know. Okay, it's getting better. So what I'm going to do is it's getting loud. I think it's network. So let's just go on. I'm using two devices here, and I just hope we'll get it done. I'll look at it in the next class. Now we know that 1 mole of sulfur is 32.0 grams. The first thing that we're going to do is to get the number of moles of 2.10 grams of sulfur, because definitely 2.10 grams of sulfur is not 1 mole of sulfur. So doing that, we already know that 1 mole of sulfur is 32.0 grams. So what do you think 2.10 grams of sulfur is? Please write that in the chat box. 2.10 grams of sulfur is what? What is the number of moles of 2.10 grams of sulfur? The number of moles for 2.10 grams of sulfur. Forget about what you're seeing on the chat box. Go to the, what you're seeing on the slide. Get onto the chat box and give me your answer. Okay, 0.0655. Good. 0.066 approximation. Excellent, excellent, excellent. I need more answers. Good. 0.0655. Good. Now we have the number of moles for 2.10 grams of sulfur, because that is what we are asked to calculate and not 32.0 grams. So that is the first thing we have established. Now, okay, it's fine. It's fine. Everybody is getting it. Let's go back again. Now remember that the 1 mole of sulfur produces minus 296 kilojoule per mole of SO2. Now, we now need to get 0.06555 moles of sulfur. What is the amount of heat or the quantity of heat that it will produce? That is what the question is all about. What is the amount of heat or the quantity of heat that 0.0655 moles of sulfur will produce? If 1 mole of sulfur will produce minus 296 kilojoule per moles of SO2, what amount of heat will 0.0655 moles of sulfur give us? So basically, the answer is there, and we know that that is minus 19.4 kilojoules. And because we have minus 19.4 kilojoules, I want to ask us, what type of reaction is this reaction? What type of reaction is this reaction? Can we go on to the chat box and answer? What is the type of reaction? Give me the type of reaction now. Exothermic. Good. Excellent. 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 It is an exothermic reaction because heat is released, and again, because the delta H is a negative, the delta H has a negative sign, and so the reaction is exothermic. Now, when we say the reaction is exothermic, is heat being released to the surrounding from the system, or heat is flowing from the surrounding to the system? Can you answer that again quickly? Go to the chat box. Heat released to the surrounding from the system, or heat is flowing from the surrounding to the system? Released from the system to the surrounding, or from the surrounding to the system? I know heat is released. How is it released? Is it from the system to the surrounding, or from the surrounding to the system? Don't give me a wrong answer. I will not be happy. Who is giving me this? Chioma, look at what you have given me. Okay. Yes. Yes. Heat is released to the surrounding from where? Okay. From the system to the surrounding. So I want Chioma to correct herself before we move on. Chioma, I want to see your answer before we move on. System to the surrounding. Chioma, you're the one keeping us. You are blessing. System to the surrounding. System to the surrounding, correct? I have 2 people to correct themselves before we go on. There is no time. We need to finish this class. So I'm waiting for the 2 of them. Okay. Okay, this is an exercise. You will get this when I'm going to send the slides to you guys, and you do this exercise. It's still the same method that we used in the last example. So we don't need to waste our time here. Let's just go on, because we have we have about 7 minutes to end this class. And we still have I have important things to discuss with us. Now let's look at this particular one. Now, in going from a particular set of reactants to a particular set of products, sometimes the change in enthalpy, is the same, regardless of how you go. Whether you get a reaction in stepwise or in a one-step series, it does not really matter how you go about getting your desired reaction. What do I mean by that? We have an example here. The equation we have here says nitrogen plus oxygen will give us nitrogen oxide. Now, the delta H is 68 kilojoule. That is plus 68 kilojoule. That means that it's an endothermic reaction. Now, this reaction can be carried out in 2 series. and you still get the same thing. You can start this reaction by reacting your nitrogen. So you know that if you react your nitrogen in limited oxygen, you have nitric oxide. Here you're using limited oxygen. You have nitric oxide. This nitric oxide will further react with oxygen to give you NO2, that is nitrogen 4 oxide. Now, these two reactions and this straight one reaction, this one went through 2 steps. This one is a 1-step reaction. What I want us to note is that it does not matter whether you go via 1 step or 2 steps or series of steps. It can be more than 2 steps. The change in enthalpy is going to be the same. The amount of heat released or absorbed is going to be the same. That is what we want to establish here. So let us look at how this is possible. Now, the example that we have here is very simple. The example that we have here, sorry, I'm not always doing this. I'm not always giving the slide the full screen. I'm so sorry. Maybe that's why you guys are not hearing me. Now, let's look at the equation again. Like I said, this is a 1-step equation. This reaction, you have equation in 1 step. Nitrogen gas plus oxygen to give us NO2, nitrogen oxide. You can also have this reaction in 2 steps. First of all, your nitrogen gas is reacting with an oxygen, but here oxygen is limited, and so you first of all form the nitric oxide. The nitric oxide will further react with oxygen to give us the nitrogen oxide. Each of this reaction, because this is a reaction, each of them will have its own change in energy. Now, addition of these 2 series of steps is going to give us what we have in this 1-step reaction. But before we go into that, what I want us to note is that when you have these 2 reactions, always know that you have the reactant side and you have the product side. Now, the way we do our simultaneous equation in mathematics, that is what we are going to apply here. What is on the reactant can only cancel what is on the product side. So what you have on the left-hand side can only cancel what you have on the right-hand side of the other equation. Now, let us call this equation, this first equation, equation 1, and call the second equation, equation 2. So nitrogen plus oxygen giving us nitric oxide is equation 1. Nitrogen oxide plus oxygen giving us nitric oxide plus oxygen giving us nitrogen oxide is equation 2. Remember that you'll always say equation 1 minus equation 2 or whatever. Now, what we have here is, first of all, if you have this kind of equation, you balance your equation. Make sure that all the equations are balanced. If you look at what we have here, in our first equation, we have 2 nitric oxide in the right-hand side, and we have 2 nitric oxide in the left-hand side. So these 2 will cancel each other. They will cancel each other, so they are no longer in the equation. Now, the second thing that we're going to look at, is there any other thing that will cancel? No. These 2 oxygen, they are in the same side. They're on the same side, so they cannot cancel each other. And you have nitrogen here, you have nitrogen oxide. They are not the same thing, so that they cannot cancel each other. So what you do now is add equation 1 and 2. So our equation 1 now here is nitrogen plus oxygen plus oxygen. Because you have oxygen and oxygen, it's going to be 2 oxygens. That is what you have here. Nitrogen plus oxygen plus oxygen. That is nitrogen plus 2 oxygen. It's going to give us 2 nitrogen oxide. That is exactly what we have in the equation that gave us a 1-step reaction. Now, the other thing now, let us now add the change in energy to see if we are going to have the same thing as when the reaction is a 1-step reaction. Now you're going to add change in enthalpy of equation 1 and change in enthalpy of equation 2, and that is 180 plus minus 112. So 180 plus minus 112 is just like saying 180 minus 112. So 180 minus 112 is going to give us what? It's going to give us 68, and that is 68 kilojoule. So we have the same thing as if the reaction is a one-step reaction. So let's look at the next example. Oh, sorry. Now, the next example, it's the formation of the reaction between nitrogen and water to give us oxygen and ammonia. Now, if you look at this reaction, you have, this is a one-step reaction. The one under is a one-step reaction. Now, this other one, it's a reaction that you have in two steps. What you have is this. There are some cases that you need to rearrange the reactant and the product, depending on what the desired reaction is. Now, let's go to the next slide so that you get what I'm saying. This is the desired reaction. The desired reaction is showing us nitrogen gas, 6 moles of nitrogen gas reacting with 6 moles of water to give us 3 moles of oxygen plus 4 moles of ammonia. Now, we now have this reaction in 2 steps. The first step is your nitrogen gas reacting with your hydrogen gas to give you ammonia. Heat is released. Then water will give you hydrogen and oxygen. Here, heat is absorbed. Now, remember, you're going to add these 2 reactions to get the desired product. In doing that, one thing you should consider is this. You should consider what the desired reaction is. Now, somebody can say, Ma, why are we not multiplying this first equation by 2? You know that if you multiply this first equation by 2, you will have just 1 mole of nitrogen gas plus 3 moles of hydrogen gas to give you 2 moles of ammonia. Good. But remember that there is no other place here. The second equation does not have ammonia. True or false? It is true. And the desired product has 4 ammonia. And you're having 2 ammonia if you use 2 to multiply this first equation. You're still going to multiply the enthalpy change by 2. But you have 4 and you're having 2. That does not represent the desired reaction. So in as much as you have your reactions in series, you must use a factor or whatever you're doing to this reactions in steps to accommodate the desired reaction in such a way that it will be a true representation of the desired reaction. Now, the only thing we can do to get a true representation of this desired reaction is by multiplying the first equation by 4 and multiply the second equation by 3. Somebody will ask, Ma, this second equation is balanced now. Why are we now multiplying by 3? Yes, it is balanced. We are multiplying by 3 because you have 6 moles of water in the desired equation. And the only way you have water is in the second equation. And the second equation has 2 moles of water. And the only way you can get 6 moles of water is by multiplying these 2 moles by 3. I don't know if you're getting me. If you're getting me, please quickly go to the chat box and reply me now. I want to be faster. Can you reply me? Quickly, we'll say, good. We'll say end the class, don't worry. We'll end the class in this one. Now, that is the only way you get 6 moles of water that you have in the desired reaction. So you can see that it is the desired reaction that is guiding us to what we are doing with these step reactions. Once we get this, we are good to go. So we already have this. On. So what we do is just multiply 4 by this. You get this 2 moles of nitrogen and all of this. Remember, I told you that what is on the reactant side will only cancel what is in the product side. That is your left side and your right side. Now let's go to the final reaction. You have 6 hydrogen gases here. You have 6 hydrogen gases here. You have to do what? To cancel the 2. And if you look at the
the desired reaction. There is no way, both in the reactant side and the product side, that you have hydrogen gas. So that is to show you that you're doing the right thing. So this and this cancel that. So there's no way you have a hydrogen. So all you need to do is to add up equation 1, the first step and the second step. So everything in the left hand side, you're going to add them, which is your 2 nitrogen gas plus 6, your 2 moles of nitrogen gas plus 6 moles of what? Water. That is what you have here. It will give you what? 4 moles of ammonia and 3 moles of what? Oxygen. That is what you have here. And if you look at the desired reaction that we are looking at, we are correct. So let's look at what? Let's now calculate the change. The enthalpy, the change in enthalpy. Remember, all these changes, whatever you do to the any factor you use to multiply here, you're going to multiply the heat change too. So this is times 4, and this is what? Times 3. So once we do that, we have minus 184 kilojoules for the first step and plus 1,452 for the second step. And when you add the two together, you have plus 1,268 kilojoules. And that is actually what you get when you carry out this reaction in one step. You have delta H as 1,268 kilojoules. I think we're going to end the class here. I have 2 more slides to go. So the next class, we are going to be very, very fast to finish up this and then go to the what we are supposed to do for the day. Thank you so much, and you have a great day. So can I hear your response before we sign off? Can I get your response? That's the end of the class. Thank you so much, and have a good day. Thank you. All right. Okay, so we have our class on Friday. What time is Friday class? Is it 8 to 9 or 9 to 10? What is the time? Yeah, the desired product will be given in any question. Okay, 8 to 9. Thank you so much. The desired question, the desired reaction will be given in the question. I'm saying the desired question. So the desired reaction will be given because that is what we're going to use as a clue to get to where you're going to. Okay, thank you so much. That's all for today. Have a blessed day.
I don't know.